Yes, good morning. Today we'll continue with numerical integration. So on Tuesday we had the trapezoidal method, Simpson method, and Romberg integration. So today we'll look at adaptive quadrature, which is a more applied form of numerical integration. So we're going to use both the trapezoidal method and the Simpson's method today. So the problem with the formats we've used earlier, they are somewhat inefficient if you want to estimate, for instance, a graph that has both, or a function that has both highly variable, large variations and small variations. So here you have a large variation. So here you need more intervals, or a shorter step length, and here you could do with a longer step length and still have the same answer. So let me just finish this. So what we are looking for here is a method where we could, instead of just having a lot of small intervals, we will have, where we need to, we have small intervals, but where we don't need it, we can have also large intervals, intermediate size intervals, and so on. So instead of just approximating this using, let's see, it's going to be down here, we will then end up requiring fewer function evaluations and also getting a okay approximation of the integral. So in this case, the error will be evenly distributed over the whole function. Instead of just, you have a huge error here, and here you have almost no error, then you would have better distribution of it. It's also, more efficient. You have a built-in tolerance or error estimation of the method. And actually, this is used in commercial software as well. So again, we have our integral, which we will try to approximate. It's going to be from a to b dx. This is going to be some kind of number I within a specific tolerance. So we want this to be, the error E should be less than, within some kind of tolerance, epsilon. So how should we do this? Well, first we can try to apply Simpson method on the whole interval. So then we will get something like, let's see, AB x dx is, Simpson's method is something like this. So f h plus an error, and I'm going to write it out this time. H over 5, 90 f of, f, fourth derivative of f, and then some kind of constant inside there. And again, this psi should be inside the interval from A to B. And again, we start with the step length. So what we're trying to do here is just estimate the whole function, the integral of the whole function, using one interval. And, we can try just doing it. So say our function stops there. And, then we will have a midpoint here. So this will kind of be our first. And you can see that's not really a good approximation. So what if you try to divide this into two intervals instead? Yeah, I should also write up what the Simpson method is for later. So S of h is going to be h over 3 f of a plus 4 of a plus h plus, as we had the last lecture. So you can see we have just evaluated the function at 3 points, which is the endpoints. So this is A, this is B, and then some kind of point in the middle, which we can call either A plus H or just C over there. So that's our first approximation of this integral. So the second step, well, we can try to divide this into 2 intervals. This might be better to illustrate with a different graph. And more simple. So we will have this. Yeah. Let's see what I had. Yeah, it kind of works. So our first approximation will be something like this. Let's see. Over there. So this is our function f now. And the first Simpson will be oh, come on. Something like this. That's our first approximation, and you see we're kind of missing, but if we're lucky here, it's going to cancel out. But that's not the point here. This could be an arbitrary function. So, yeah. So now we want to try to approximate this using, instead of just this one interval, we will introduce 2 intervals. So we will instead try to use these points. That's going to be up there, and this is going to be down there. So here we will have, let's see. So here you see we're actually fitting the function a lot better than what we did earlier by just splitting it in 2. And we can also use this to try to estimate this error in a better way. Where's my chalk gone? So basically what we're going to do now is that we will apply Simpson's rule on this, well, basic. So now we'll have 2 intervals. That means that 2m equals 4 because m is the amount of intervals, but we will still keep our old h. Yeah, but oops. Keep the same h, which means that in our interval here, the first one, h was this. Whereas in our second, we will have, let's see, this is going to be h over 2, h over 2, h over 2, and h over 2. So we are keeping the same step length, like the h constants, but, well, it is the half step length, so we just introduce this. And if we try to do the integral with this using, well, again, the Simpson method, dx we will get h over 6 f of a plus 4 f of a plus h over 2 f a plus h. Let me see. 4 a plus 3h 2 plus f of b, like so. And in this approximation, we get the error h over, no, not squared, the power of 4, b minus a over 180. And now the psi is going to be a different number, unfortunately. AB. So the problem here is that, well, this number and this number, they are slightly different because it's a different approximation. I mean, we don't really know what this psi is. This is just some kind of number inside our interval in order to actually fulfill this equality. But what we can try to assume here is that these two are actually, well, approximately equal. That is what all of this hinges on. But we can split this into also 2 in order to save some time. So we call this S of A plus B over 2 plus S of plus B over 2 to B. And then again this error, which is going to be 1 over 16 h over 5, 90, like so. So this is the expression for the whole interval. Well, I tried to make it yellow, but I see this is kind of messy. And this is if we split it into 2. And by assuming that these are the same, no, the one with the tilde and the one without the tilde, we see that we can kind of estimate the error using this. Let's try. Can I remove this? Okay, so now we have 2 approximations of our integral with a different error. I mean, they do look like each other. The only differing factor is this 1 over 16, which we get from altering the step length. So in order to get any further here, we have to assume that this xi and xi tilde is approximately the same. Oops. Is approximately the same. So this means that we can actually compare these error terms. So now we get a plus b over 2 of a plus b over 2 to b minus 1/16 H 90 is approximately the same as just evaluating it at one space. Let's see, minus h power 5 over 90 f 4 yes, this. And then we can just do some algebra, and we see that the integral to be x dx minus a minus. So this is the error of the actual real integral and our approximation using two intervals. B over 2 to b is approximately 15 times better than, let's see, as a, oops, a b minus this same a plus b 2 minus s of a plus b over 2 b. So what does this expression tell us? This big expression. Well, so this is the splitted interval is approximately 15 times closer to the real integral than what just using one integral is to approximating this. Did that make sense? I guess not. No, this is, so you have this expression here. This is closer. This is about 15 times closer to the integral than it is to this approximation. So it means that if you actually split the interval into two intervals, you will get a 15 times better approximation. Does that make more sense? So this approximation approximates the integral 15 times that it approximates the approximation using one interval. Oh. So I'm going to write this down in a better way. AB minus of A B over 2, this is the midpoint, minus S A plus B over. This is supposed to be an A to B. If this is less than this 15 epsilon, so this is how close we are, the tolerance we have, is the epsilon, then we expect that x dx minus this same two interval approximation minus s a plus b over 2 b less than 15. Yeah. And since this is a tolerance, so if we have that this expression is less than 15 times a tolerance, then we can say that this expression is actually less than a tolerance, meaning that splitting it in two approximates this in a better way. So we can actually calculate this expression because we have this approximation. That's just a number, which we've, well, gotten. This is just a number, this is just a number. We don't really know what this is, but we know that this is less than, if we know that this is less than 15 times the tolerance, then since we also know that this expression approximates the integral 15 times better than it approximates this known thing, then we can say that, well, this will again approximate our integral 15 times better. So we can actually estimate the error using this expression. And if this expression is actually less than our tolerance, then this will be 15 times less. So I'll try a simple example, I think. Yeah. Can I remove this thing? So we want to consider the integral from 0 to pi half sine of x dx, which we know analytically to be 1. So then we can actually test this. If we try to have the one interval Simpson approximation, which is this, so again, this is our full interval endpoints. This is going to be pi 4 over 3 plus 4 sin pi 4 sin pi half. And jotting this on a calculator, we see that this is, well, it's almost correct, but it's slightly wrong. 0, 0, 0, 13, 46. No, sorry, that was the wrong number. That's for two intervals. This is 0.22799. So I mean, it's fairly okay, but we can do better. Now if we try the two interval approach, plus s of pi 4 to pi 2. This is going to be pi divided by 8, 3, sin 0 plus 4 sine pi 8 plus 2 sine pi pi 4, 3 pi 8 plus 10 pi half. I mean, this isn't really important bits. This is just what we're actually punching in a calculator. But $13.46. So yes, it is a better approximation, and it should be about 15 times better. I mean, just looking at the numbers, does it seem 15 times better? It is actually more than 15 times better. So yes, if you just remember what's right there, we see that so this is S of 0 pi. So now I'm just filling in what was just on the blackboard. S of O pi 4 minus S of pi 4 pi half. You see that this is 0.0001430, whereas this other one, so this is our approximation, whereas the real value of ES is, well, then we have the integral again. Pi half, was it? Sine x dx minus, well, it's just this number, but sub O pi 4 pi 4 pi half equals 0.1346. So this is a real error, because in this case we can actually fully calculate the integral, because we're lucky, well, it's constructed, and this is our estimation. So see, they are fairly similar. Our estimation is actually giving a more pessimistic error, which is a good thing, because error analysis is all about pessimism. If you're too optimistic and it doesn't pan out, then you have a too low error estimate, and that could be, well, it could actually be fatal.
Does 1 hour estimate the error second marginal error?
No. So in this adaptive quadrature, what's it called? You see, this is an approximation, and this is the actual real error. And you see, this is bigger. So that's actually good. But then again, this is just a constructed example. But in general, I mean, as long as you have a nice behaving function, which most of the time you actually do, then this works. Yeah.
But shouldn't it be 15 times more than the...
Yeah, it should be, but that's because we had the approximation. Oh no, you think this thing?
So it should have been like... Well, this was the drive before it stated that if we have epsilon, so that the first line is smaller than 15 epsilon. The second line should be smaller than just 1 epsilon, which means that in this case, epsilon means is what exactly this number is 0.0001430. The second line should be smaller than this line.
Yes, it should be smaller. Did I miss? It could be I missed a zero. No, I didn't.
think the 15 epsilon is the maximum number of errors.
Yeah.
So actually it can be less than 15.
Yes, it can be less. Yes, that's the thing. This is less than 15 of the error. That's all it's saying. And it is, well, but it's an approximation in this case. And apparently it's a gross underestimation. So this is less than 15 epsilon, then this is less than epsilon. So it depends on your tolerance, though. I think it's easier to explain this as an algorithm, though. Yeah. So how do you actually do this in practice? Do any of you know? Do you know about recursive relations in programming? Have you ever done a recursive relation? It is where a function applies itself. No? Okay, then we'll get it. Because you can implement this in, maybe that was a bit too quick, but you can implement this in many ways. The one that is, well, saves the most memory, and I think it's also fairly quick, that is by using a recursive relation. It saves time coding it up, and it saves memory because you don't have to save all of the numbers. So, algorithmically, how do we do this? So we will have, I think we have 6 steps. Step 1. Well, we have to calculate the step length, so, well, control b minus a over 2. And then we have to evaluate the functions at point C. Oops. Evaluate, eval. At points A, B, and then we're going to call this midpoint C, which is A plus H. Which means that right now we have the interval A, C, B, like so. That's our interval. So it's not alphabetically. C is in the middle. So evaluate this function, this means basically we will save a number fa, which is f evaluated at the point A, and f c, which is of a plus h, and we have an f of, no, fc, and we have fb, which is f evaluated at point B, like so. And then we need to actually provide our function with an estimation of the integral to kickstart it. So estimate the integral. This will be I h over 3 fa for fc plus fb, like so. And then we have to give it which level we're at. So now we're at the top level. I'm just going to do this at 0. This is the level we're at. Second step. So this is kind of just an initialization. We need the step length, we need our function evaluation because, well, we want to avoid evaluating a function over and over again. So that is why I do a function evaluation and then you save it to a variable, fa, which we'll send in. So now we begin the recursion. This means that we are going one level down. So n equals n plus 1. I can maybe give, and then we need to find a midpoint. Well, that's actually wrong. Yep. So I'll save this. Yeah, I need this. So I need this midpoint, C, which is just 0.5 times A plus B, or basically just A plus B over 2. This should be my midpoint. And then we are using the same H, but we are halving it. This is, this is a programmatically operation. This isn't H is equal to H half. This is set this new H to H over 2. So imagine this is programming, right? Then we need to save, can you see this? Yes. 2 new function evaluations, which is f of plus h. Remember that h is now half of what it used to be. And f of e, which is f of a, not 2, but a divided by plus 3h. So how does our interval look like now? Well, now we have a, d, c, e, b. As you might have noticed, I don't know the alphabet, but this is just to keep track of what we have. So the endpoints is still A and B, then C is our midpoint, and then D is the midpoint between A and C, and E is the midpoint between C and B. Yeah? So then I need an estimation of the left and the right subintervals. The left one is going to be h over 3 fa plus 4 fd plus fc. Because then we've used, well, we're splitting it here, so now we're estimating for this, so we're using A, D, and C for the left one, and for the right one, we're using 3, C plus 4 FE plus FB. So. And then we need to calculate the error, which is the abs of our first estimation, which is I minus I left minus I right, like so. So then we have the start. I'm going to call this step. Yeah, so step 2 is just begin the recursion and actually do it. Step 4. Well, first you have to check if you're not deep enough, because if your integral doesn't converge, then you want to stop. So if your integral doesn't converge, then it doesn't matter how small your intervals are. So that's why you want a level control. So if n is bigger than some kind of n here, this is the deepest level you can go, then you want to end the routine. Throw error, which basically means that, well, it didn't work. I mean, either the integral doesn't converge, or you're not able to obtain the required tolerance using this method. So you should just stop. Just tell the user that, sorry, I can't do this. Don't give him a number, and just continue. And then continue, so else if, so then we're checking if this error is less than 15 times, well, that's actually the tolerance. Then we say that the integral is I left plus I right. And you can actually do slightly better here. So I haven't covered it yet. It's something called Richardson extrapolation, which gives you a more accurate answer. So I won't go through the math, but if you do the correcting term I left plus I right minus your first estimation and divide this by 15, this actually gives you a slightly better approximation. And I mean, you already have these numbers, so why not use them? Okay, so if this is true, then you're happy. Then you can go up a level again. So you can just return this answer, and then you said, oh, I'm accurate enough down here, so we're fine. It's good. The interesting bit is in the else. Which is, I'll show this in MATLAB. So I'm just write it here. So you have to do both the left and right. Try again. So how you're basically saying that I need to divide my subintervals into smaller pieces. So if you just apply this function from step 2 again, then you will get smaller intervals and a better result. And try again. Steps 3 to 5. So actually this is step 5, sorry. Step 5. Like so. And then after a break, I'll show the implementation of this. And then we will basically go through the algorithm again, but only in a more programmatically way. Any questions?